Welcome to a special seminar by Christian Keil, who is on his way to AGU. That's why it's on an unusual time and day. Christian studied in Karlsruhe in Germany, and during his studies he spent some time at Oregon State. He then did his PhD in Munich at the Ludwig-Maximilians-Universität, and together with the DLR, which is the German NASA. After his PhD, he spent some time as a postdoc at DLR and was also as a scientific consultant at ICMWF for a few years. Since 2009, he is a research scientist and a lecturer at LMU with George Craig and his group. Christian is well known for his work on convective scale modeling and prediction, with an emphasis on flow dependence. This is something he will be talking about today. And we are also working together with Ihan on some model error. This is not going to be the main topic of this talk. And in his free time, Christian enjoys to ride his road bike, although he opted for the car to drive with his daughter to AGU after this. Welcome, Christian.
Thank you very much, Judith, for this nice introduction and for the invitation and the possibility to stop over here on my way to AGU, as you said. It's an honor to speak here at NK M-Cube. And so the work I present today is mainly performed by two PhD students of mine, Matthias Pu and Takumi Matsunobu. They are employed in this Waves to Weather project. That's a big collaborative research center in Germany. I don't know if you heard about this. That's a 9-year program where we fund for 4 years roughly 30 to 35 early career scientists, not only in Munich, but as well in Karlsruhe and in Mainz and some other universities. And this will terminate by mid of next year, this project Waves to Weather. Today, I'd like to talk about the flow-dependent forecast uncertainty, especially of precipitation at convective scales. And I'd like to acknowledge, next to my PhD students, 2 colleagues of the German Weather Service, because we did a project together with them, you will see, and then the chair of theoretical meteorology in Munich, George Craig. So it's not new for you, and you know this, that forecast uncertainty at convective scales largely depends on the prevailing weather regime. But the challenge is, how can we identify the characteristics of the individual meteorological situation that impact the forecast uncertainty or predictability? And let us start with a movie, a satellite movie of Meteosat 2nd generation in the visible channel, 0.6 micron channel. I could look for forever, or stare forever at this slide. I mean, you see a lot of different cloud formations here over the North Atlantic. You see cloud bands associated with synoptic fronts. And then over mainland Europe, you see the typical sign of the diurnal cycle. So convection is developing during the day, especially over mountainous regions in southern Germany and the Alps, and then in Italy as well. And this is a weather situation which is usually not very well predictable in terms of precipitation, and that's one of the foci of my current talk. This is, for the same day, the radar observed daily precipitation accumulation, and you can see that there's a lot of structure in the accumulation. The accumulation reaches up to 50 millimeters in 24 hours, and that's on the scale of 500 kilometers here. The satellite image is on synoptic scale, so entire Europe, roughly 5,000 kilometers. And if you compare this observation to the model, you see that the model is able to reproduce the precipitation, but there are gaps in between. There are holes where the model is lacking precipitation, and we ask ourselves, how can we improve this? So my hypothesis of this talk is that convection during these weak convective forcing weather situations is less predictable, and I try to convince you today and to quantify this, that this is the case. So I structured my talk in three different chapters, so to say. First, I want to show this measure of flow dependence, that's the convective adjustment timescale. Then I will present the PSP scheme, a new stochastic perturbation scheme. Finally, we look at the scale dependence. So we look at the flow dependence and scale dependence of precipitation forecasts, of hourly precipitation forecasts. So let's start with this measure of flow dependence. Dunn et al. In 2006 proposed the convective adjustment timescale, which is a measure of the extent to which the convection is in equilibrium with a larger scale forcing. And this convective adjustment timescale uses an estimate of the ratio of CAPE and its rate of reduction of convection as a quantitative measure of the degree of equilibrium. And this removal of CAPE can be expressed by precipitation. So it's essentially the ratio of CAPE divided by the precipitation rate. And we applied this convective adjustment timescale on different data sets. This is a pretty old work we did on observations of radio sondes and radar observations for 7 years over Germany. And we have here on the x-axis the convective timescale in logarithmic scale, and on the y-axis the frequency. And you see if we choose a threshold between 3 and 12 hours, here I've chosen 6 hours, that the majority of the events happens during strong forcing, and that less often we have weak control of convective forcing.
So you basically include all the sources of CAPE into what you call forcing, am I right? Because of the definition of the standard.
Exactly.
So surface fluxes, the large scale, vertical motion, everything is kind of put into this definition.
Into CAPE, but the removal of CAPE, this is only by precipitation, exactly. And then by the latent heating or latent heat release of precipitation.
That goes back to Arakawa, in fact, am I right, in a sense?
Yeah, Arakawa to Schubert. Okay, yeah. It's probably cited in the work of James Dunn as well, yeah, but you're right. And the different regimes, the strong and weak forcing, can be regarded extreme of a continuous distribution. There's no really a scale break, but in many applications we use 3 to 12 hours at the threshold to distinguish between strong and weak forcing situations. And these are two images, two figures, which show the spread of area average precipitation over Germany. And on the x-axis, you have again the convective adjustment timescale and logarithmic scale. And here you have the spread, but the normalized spread of precipitation, because precipitation has a large variability, as you know. And you see that there's a positive correlation between the convective adjustment timescale and the spread. So the larger the convective adjustment timescale, the larger the weak forcing is, the larger we have the spread. And this positive correlation is 0.75, so it's a pretty strong correlation. And actually in an earlier work, we looked at an ensemble system of the German Weather Service, where we stratified this ensemble system into different sub-ensembles and could identify that the black one is the model error sub-ensemble, could identify that the model error is more important, that the spread of precipitation, again, the normalized spread of precipitation is higher during these weakly forced situations. While the lateral boundary conditions, this is LBC, this is always equally important. So there's a strong flow dependence of the importance of the model error in these convective scale models. So to wrap this first part up, we think that the convective adjustment timescale is a robust metric for categorizing and classifying the convective weather situations, and is suitable to examine the flow-dependent behavior. Now I come to the second part, And I'd like to present you the stochastic boundary layer scheme. That's a very general graphic here. That's not new for you. That convective scale or convection-permitting EPS allow the estimation of forecast uncertainty or predictability. And you need to represent different sources of uncertainty in this system. Very important are initial condition and lateral boundary condition uncertainty. The problem is that the convective permitting ensemble prediction systems are frequently under-dispersive. That's why we need some formulation or multiple formulation of model errors. And this under-dispersiveness is sometimes a consequence of the incomplete description of the physical processes or an insufficient representation of subgrid scale processes in the model. And if you look at moist convection, precipitation, then the representation of boundary layer turbulence is important to trigger convection. And in traditional parameterizations of boundary layer turbulence, they were developed for grid sizes that are large relative to the size of individual turbulent eddies. And they are designed to represent the mean effect of many eddies, and the variability associated with the individual eddies is averaged out. However, if you go to the kilometer scale, so convection-permitting models, these models contain only a small number of large eddies and in a certain grid box, and their variability can have an important impact on the grid box mean if the grid box is only 1 kilometer wide. And this results in an underrepresentation of variability on the smallest resolved scales in the model, which are especially important for convection triggering in the weak forcing regime. And the physical-based stochastic perturbation scheme, short PSP, was developed to reintroduce the influence of this lost small-scale variability by adding perturbations to the tendencies of temperature, humidity, and vertical velocity on the smallest effectively resolved scale. And this effectively resolved scale is 5 delta x in our approach. And so the tendencies are written by this formula, and this formula combines the subgrid standard deviation that comes out of the turbulence schemes of the icon model with a random horizontal field. Eta is here this random horizontal eddy field, and these are multiplied with some other constants. And an example how these two fields look like, you see here at the bottom. This is the random field, which is constant for 10 minutes and has this effectively resolution of 5 delta x. This is multiplied in this example of the subgrid standard deviation of the temperature field, and this gives then this perturbation fields, which is added at the tendencies of temperature, humidity, or vertical velocity.
They still have a relatively large scale, am I right? If you look at the previous picture, those are relatively large scale perturbations still. This is.
Yeah, but I mean, the effective resolution is the resolution the model sees, right? If you go below the effective resolution, then it's just noise and it's averaged out somehow. And in comparison to other schemes, for example, the microphysics schemes, they use horizontal scales of 100 or 150 kilometers in their random field. So that's a fairly fine random field, I would argue.
How do you generate that?
That's with a random number generator. This field, this random field.
But you have it at a particular scale. So how do you impose that scale on a random number field?
Yeah.
Wait, my comment, perhaps related, is that
Please use the microphone.
in a small-scale modeling, we used to do those perturbations Because if you look, for example, at the boundary layer graphs, if you don't have perturbations and you just have surface fluxes, you can run it for 100 days and nothing will happen. Basically, until the round of error on your computer simulation grows up to the scale that matters. So we put this 10-degree, tenth of a degree temperature perturbation in an LES kind of simulation. So, but those are really done at the grid scale, and you basically put random numbers. So that's a little bit different to what you. First of all, you perturb tendencies, not the fields itself.
Exactly.
Which, of course, when you apply it, you have, yeah. But the Bill's question, I think, is related to my question. That this is fairly large scale. This is. Well, perhaps we should ask what kind of a resolution model you use. This is convection-permitting simulation, am I right?
It's 2 kilometer resolution and 5 delta x, that's then grid length, exactly. And effective resolution is then 10 kilometers. Yeah.
There was also the question how you get these spatial perturbations. There's a number of different pattern generators that introduce spatial correlations. Typically, they act in, they are developed in spectral space. This is just one of them. And this is the one from Wafer and Courtier that has been originally developed for in data simulation and is widely used to generate spatio-temporal perturbations that you can control, so they're Gaussian in space and time with a prescribed length scale.
Okay, thank you, Judith. I think I move on. So we tested then this stochastic PSP scheme in the icon model, the icosahedral non-hydrostatic icon model of the German Weather Service with 2 kilometer resolution, 65 levels, and the model top is at 22 kilometers height. We have 20 ensemble members in this ensemble prediction system. Initial condition uncertainty comes from the Kenda system, kilometer scale ensemble data simulation. This is based on the LATKF of Hunt et al. And the lateral boundary conditions, hourly lateral boundary conditions, stem from the driving model, the Corsa grid model with 13 kilometer resolution, which is covering the entire European domain. And the ICON EU EPS, it's a global model. We run the experiments for an entire summer season in summer 2021. And we started runs daily at 0 UTC and have a forecast hour, 24-hour forecast hour, and use hourly output. And we have two simulations, the reference simulation, which is mimicking the operational forecast, and then the one where we added the stochastic PSP scheme as a representation of model error. In the reference simulation, we have perturbed parameter, the perturbed parameter as representing the model error. And this was done in collaboration with the National Weather Service, and it was run on their high-performance computing. And now we expect to see that the PSP perturbations have a larger impact on convection when this is triggered by local scale processes that are driven and that are not driven by some larger scale forcing. And there we now apply this flow-dependent classification and use this or categorize these 3 months of data into flow regimes. We took a relative approach and said the top 20% of the distribution with the highest numbers of the convective adjustment timescale make up the weakly forced situation or the weakly forced composite, and the bottom 20%, the strongly forced situation. And here you see images which I've shown you before. New is here the middle one. That's the PSP run for this 10th of June 2021, which is a weak forcing case. And you see that we have a little bit more precipitation here in south central Germany compared to the operational forecast, where we have here this kind of hole where we don't have any precipitation. This is the radar observation. And this is now the weather regime dependence of precipitation. On the left-hand side, you see the weak forcing composite. This is based on 16 different days. In red, you see the results of the PSP experiment. In black, the reference. And you have here the bold lines is the ensemble mean precipitation. So you see the PSP triggers precipitation earlier. we have an earlier onset of precipitation and a slightly higher peak, whereas the total precipitation amount is only changed by plus minus 3%. So the total precipitation is hardly changed. What is more impressive is that we have a largely increased spread of precipitation, which is earlier and coincides with the peak of the ensemble mean precipitation. And this is visible only in the weak forcing situation. If you look at the strong forcing situation and first look at these straight lines, you see no clear daily cycle, or you see in fact no daily cycle. You see little effect, very little effect of the PSP scheme, and the PSP only slightly shifts the peak to earlier hours. By the way, UTC time in Europe, 12 UTC is 14 local time. So this is more or less then the peak of precipitation is in the early afternoon. So this was the weather regime dependence of precipitation. Then we looked at other near-surface parameters and compared them with standard synop observations for this entire 3-month period. So this is not flow-dependent, this evaluation. And we looked at different quantities or measures for 10-meter wind, low clouds, 2-meter temperature, and 2-meter dew point temperature. And I hope you can read it. It's fairly small, but here in the spread skill relationship here on this line here, you see that the model is underdispersive, what I said before, and that the red line, which is again representing the PSP scheme, has a higher spread skill ratio, which is closer to 1, so improves or reduces the underdispersiveness. At the bottom, which already showed up, I have the probabilistic CRPS score, where you see hardly any difference, and the root mean square error only shows very slightly differences. So in the middle is the mean error for these 4 parameters, and you see that the mean error is improved for low clouds. Low clouds are here, so in this column. And if you look there closely, the red line is closer to 0. So here the mean error is reduced for low clouds. However, if you look at 2-meter dew point temperature, we have a larger error, a larger negative error in the 2-meter dew point temperature. And this was an effect which is not wanted, and this prohibits the operationalization of this scheme at the German Weather Service. So we looked a little bit more into depth in this problem, and we looked at 2-meter dew point temperature and low cloud cover on dry days. And you see here, that's a scene of one single day where we had no precipitation but low clouds. And you see here the reference field of the low clouds, and you see that this PSP scheme breaks up these continuous cloud fields and generates somehow holes in this cloud field, and this is then the consequence is then a dry bias in the 2-meter temperature. We have an idea how to cure this, and this is now ongoing work in collaboration with the German Weather Service. This is here the vertical profile of the PSP perturbations. So we have maximum perturbations in the boundary layer, and then at the top of the boundary layer, we relax the perturbations to 0. And we lowered this relaxation and have it now within the top of the boundary layer, so we don't have so much entrainment of dry air into the atmospheric boundary layer, and this reduces this breakup of clouds. And we run now longer simulations where we apply this new vertical tapering profile with the PSP scheme. Summary second part, we think that the PSP scheme provides a good representation of the effect of subgrid scale turbulence and improves the ensemble forecast for near surface variables. So not only for precipitation, but as well for 2-meter temperatures and the other variables I've seen during weak control. And during strong control, which is dominating the weather, there's a negligible impact. So finally, I'd like to look at the scale dependence, and we look at the scale dependence in parallel to the flow dependence. And to assess the scale dependence, we use the fractional skill score and apply the fractional skill score as Roberts and Lean developed it. On the one hand, we compare observations and forecasts. Here on the left-hand side, I have again radar observations and the reference forecast. We compare this in this entire German domain in Central Europe. And we look at different sizes of the search windows and look how many grid cells in the search window then exceed a certain threshold or a certain percentile which we applied. And, and this can be as well used to compare two different forecasts in the ensemble, and then we get an impression or a result on the ensemble dispersion or the ensemble spread. So we use it to show the error, the spatial error, and if you compare two ensemble members, then we can look at the ensemble spread, the spatial spread. And this is one image to show the scale-dependent error. This is now, again, the 16-day composite of weakly forced situations. Let me guide you through this figure because it's a pretty busy figure. Here on the left-hand side, you see the 95th percentile of precipitation. So to remove the frequency bias between observation and forecast, we use the 95th percentile of hourly precipitation. And here you see nicely the diurnal cycle with the maximum around 15 UTC and a minimum here before convection is triggered. So the blue line represents the 95th percentile of precipitation. In color code is 1 minus the fractional skill score. So the brighter the color, the better the forecast quality is. So you see that the largest spatial errors occur on the smaller scales. This is not surprising, right? You see here the time series, and here on the y-axis you see the spatial scale from model resolution 2.2 kilometers up to 300 kilometers. And you see here this diurnal cycle as well in the value of 0.5 fractional skill score. That's a value which Roberts and Lean said that's kind of the believable scale, and that's a scale where we can say the forecast performs sufficiently good. And you see here the peak in spatial error at the onset or before the onset of precipitation when we have very little precipitation. But then once convection is triggered, then we have a better spatial forecast skill, which is around 50 to 90 kilometers. And you see as well this typical diurnal cycle then in this error metric as well. So this is the situation for the error. Then we can look at the spread. So the top panel is the same. The bottom panel is now the spread in color-coded. Blue is the same line, this is the 95th percentile. And the dashed line is the same as here, that's the error. And this is here the ensemble spread. And you see that the ensemble spread is smaller than the error. That means that the ICON D2 forecasts, and this is the operational forecasts, are spatially underdispersive. And we have here a scale break of, let's say, a couple of tens of kilometers where the model, the spatial error of the model is larger than the variability within the ensemble forecast. This is for weak forcing. And if you look at, and this underdispersiveness tells us that we need additional sources of model uncertainty in the model to reduce the gap between the spatial spread and the spatial error. And here on the right-hand side, you now see the other forcing regime, the strong forcing regime. You see the diurnal cycle. You saw no diurnal cycle. You see the diurnal evolution of precipitation of these 16 days, which is pretty flat. The values are much larger than during weak forcing. Here we are in the range of 0.1 to 0.3 millimeters per day, and here it's around 1 millimeter per day. But the error is again here. The error is again larger than the spatial spread. So it has, in strong forcing, the model has a better forecast skill, but we still see this gap between the spread, the spatial spread, and the spatial error. And you can guess what comes next. This is now the experiment where we included the PSP scheme. This is now PSP minus the reference run. I go back and forth. So the dashed blue line is now the reference 95th percentile, and the blue thick line is the PSP 95th percentile. You see what we already discussed, that we have an earlier onset of precipitation and a higher peak during weakly force situation. What is interesting in this plot is if you look here at the top left panel at first, we see that the PSP reduces the spatial forecast errors at scales larger than 20 kilometers. If you look closely here at scales less than 20 kilometers, we see an increase in error, but that's not surprising because we add there the perturbations and at this effective resolution, and they obviously result in a larger spatial error. But it's, as soon as we look at larger scales, larger than 20 kilometers, we see smaller spatial forecast errors. If you look here at the left bottom panel, there is the spread of precipitation shown. We see that the PSP increases the spatial spread at scales smaller than 50 kilometers. And you see, if you look closely, the upscale growth of this spread. So the spread is, as I said, introduced at the effective model resolution at 10 kilometers, and then it's largely, or it's slowly growing to a scale of maybe 40 to 50 kilometers during the diurnal cycle. And the PSP decreases the spatial spread at scales larger than 50 kilometers. And there we looked at spatial fields, and we've seen that PSP is much more active generating precipitation and moist convection over topography, over orography. And if a lot of members produce this precipitation cells over orography, then the spread is smaller. And that's mainly this effect we see here. On the right-hand side, for consistency, I show again the strong forcing situations where you see that the differences are much smaller. The differences are mostly blue, so it's beneficial, smaller error and smaller spread. And yeah, right. So this brings me already to the conclusions. So we think that the flow dependence is an important characteristic which needs to be taken into account if you look at convective scale predictability, and that the convective adjustment timescale is a robust metric to distinguish these different flow regimes for convection. We've seen that the forecast uncertainty is larger during these weakly forced situations where local trigger mechanisms like conversion zones or so are necessary to get the convection going. The PSP scheme provides a good representation of the effect of subgrid scale turbulence. And the scheme improves the ensemble forecast, not only of precipitation, but as well of near-surface variables during weak control. During strong control, this difference is negligible. And in the third chapter, I've shown this spatial view on forecast quality and forecast spread. And I've shown that you need to look at beyond the grid scale to get the full appreciation of the impact of this scheme. And we've seen that the PSP scheme, if we use it in the ICANN-D2 EPS model, reduces the spatial underdispersiveness. Let me finish with a view on ongoing work. PhD candidate Ihan Chen, who is working here at NCAR, together with Bill Kuo and Judith Berner and George Craig in Munich, applied the convective adjustment timescale for, I think, 4 years over the conus domain, and could identify different forcing situations in these different regimes. And in the second work, we look at the upscale error growth of different model error formulations. She implemented the PSP scheme in the Worf model, and then uses as well the microphysics perturbations of Greg Thompson, and we compare in which flow situations which perturbation has a larger impact of the forecast variability and the forecast quality. With this, I'm at the end of my talk, and I thank you for your attention.
Thanks very much for your talk, comprehensive talk, Christian. I also, before I forget, want to say for the people who are here in person, we're going to have lunch after this, and you're welcome to join us if you're interested. Let's start with questions. We have one online by Morris Weisman. The dependence of convective adjustment timescale on precipitation seems to ignore the potential positive impact of precipitation on convection via development of cold pools, which can contribute to the regeneration and sustenance of the convection. Have you considered this role of the cold pools?
In the calculation of the classification of the different flow regimes, we didn't consider the role of cold pools, but in the Waves to Weather project, we developed a cold pool scheme which mimics the impact of cold pools from existing convection, and which enhances then the triggering mechanisms of convection. But cold pools are not considered in the description of the convective adjustment timescale.
Any questions in the room? Sorry.
Thanks, nice talk. I have a couple maybe more technical questions, and one of them is about the convective timescale. So what is the area that you assume for the calculations, or that you use for the calculations of CAPE and P? Because I imagine that is quite important for this. And then as you get to larger and larger scales, the precipitation will depend, it's kind of a proxy for convective area. And when I think of strong forcing, I think of some kind of triggering mechanism for the convection. And I'm guessing that as you get higher precipitation, in that case with a large area of convection, it means that there's more kind of focused areas of triggering. So is that the basic idea here?
Exactly, and I missed it. We actually smoothed the field with the Gaussian kernel, which has 30 kilometer half width. So the convective timescale describes the ambient environmental condition where the convection develops. It doesn't vary from grid point to grid point, but has these 30 kilometer.
Okay, so it's a 30 kilometer scale,
exactly,
smoother.
Yeah.
Okay, got it. The second question is about the PSP. I'm assuming the perturbations that you're applying on the boundary layer have a mean of 0. With that?
Yes, right.
Okay, if you go back to the plot, sorry for making you go back, it looked like there were more positive than negative ones. Okay, Judith is shaking her head, yes. Yeah, so I'm trying to understand that in the lower right plot. It looks like, I don't know, maybe that's just the scaling, or,
I think it's
the color
probably the
scale.
perception of the human eye that you maybe see the blue. No?
I haven't.
Okay.
I could hand this over to Ihan, but we looked into this. There's a hysteresis effect. And so it turns out that it's easier to trigger convection than suppress it. And so basically you have a lot of potentially unstable, the amount of cells that are just below the level is a lot larger than those that can be suppressed. And so this is why there's this systematic effect of the precipitation happening earlier, and there's also more precipitation. So this is an example where a Gaussian perturbation leads to a systematic impact with a systematic mean, and it has to do with it's a hysteresis effect of the state.
I don't quite follow that. I thought the lower right plot was just the perturbations themselves, but I don't want to monopolize the time here. We can talk about it offline.
No, I see what you're saying. So I'm sorry if I was wrong about what that plot is. So,
Yeah, I don't think that's the precip impact, right? That's just the perturbation.
yeah.
That's DDT of the PSP, right?
Yeah, but at first you were discussing this one, right? And there you would say it's more yellow than blue?
No, I'm saying the one.
Oh, the one on the right. Okay, right.
The
Okay.
lower left one looks like it's a mean of 0.
Okay. Then I missed it.
Because I understand the lower right one is the perturbation. It's actually being applied.
Exactly. Yeah.
I'm not sure. Good
Okay,
point.
anyway,
but,
yeah,
but
that's-
yeah,
we
what
can
I said is the
talk about
case,
it
but I don't know what that plot is. Sorry about that. Yeah. So there's a question from Chris Snyder. He says, I don't understand, or I didn't understand the discussion of the FSS in relation to spread. Could you explain further? Are you computing FSS for each member? I think this might be your slide 27.
Slide 23.
Oh, sorry. Maybe, yeah.
Yeah, actually, we compare member per member without any observation. And if you compare these 20 members with each other, then we do this 190 times, and that gets for one forecast time a mean value of the fractional skill score. And this is then done for any hourly precipitation field, and then we get the spatial spread out of this. So it's this spatial dispersion, or the spatial spread of the precipitation field, which we use there. Originally, as I said, this score was used to detect a spatial error, where we compare then the observation, but you can use it in both ways. And they all did it the first time in their ensemble to compute then a spatial spread.
I actually had a question about slide 27.
Okay.
Where you show spread and error, and it's nice because you have this diurnal cycle in there, and I thought, oh, if you go to the one before, not that it matters, it's fine. I thought it was really nice that the spread in the lower left one, you also see at least a hint in the spread of that peak error at like 9 UTC. I thought that was nice. But if I look at this, the first thing I thought, if I compare the spread and error for the weak convective cases, it seems that the error at initial time, at time 0, is already so much higher than the spread. Do you understand what's going on there? I would have thought this is a scheme where the DA isn't then working properly. If it's so underdispersive at time 0, I wonder if something's off with the initialization.
That's a good point. No, we haven't looked into this, I have to say. Yeah.
There's the strong forcing cases, that makes sense, and so maybe the DA is somehow tuned implicitly more to the average case and more impacted by the strong ones, and so you grossly underdispersive for weak forcing cases could be interesting to look into.
Yeah. I talked to the PhD student. Thanks.
Yeah, Craig.
Thanks for the talk. So in the PSP formulation, you have this alpha tuning. Can you explain how difficult it was to tune this PSP scheme to get the results that you got?
Ian is the expert in tuning this. What was the approach, Ian? I think we used this. We tested this tuning parameter in the weak forcing regime and wanted to have an impact of the PSP scheme, which is as large as the observation, exactly. So we varied this tuning parameter between 1 and 10, I think.
Actually, I think it's very sensitive.
Please use the microphone.
Yeah, so we try to match the forecast with the observation, radar observation, and the tuning parameters range from the points, I think until 0.5 to 5, and it's quite sensitive. like the precipitation will like increase proportionally.
And actually, I think in WRF you have a different alpha. Two, right? Okay, yeah. So you did the tuning in WRF of the PSP scheme, and there we get a different alpha parameter.
But if I understand correctly, a key point is that this alpha tuning is not done based on spread error, which a lot of schemes are tuned towards, so that you get the right spread at the forecast lead time you're interested in. But this tuning parameter is really done as much on first principles as possible.
A quick clarification. So the subgrid scale standard deviation, which I think is quite important in here, that comes from whatever, like TKE that you have in a model, things like that.
Exactly.
It's never tied to observations, for example, like some temperature or moisture fluctuations in observed boundary layer over forest or over lake or whatever, which would be also something to consider, am I right? Because we know how uncertain the subgrid scale parameterizations are and how sometimes remotely they are compared to the real world. So that's
You are totally right. I mean, but we took this from the turbulence scheme exactly, and yeah.
Well, if there's no more questions right now, let's thank the speaker again. And feel free to join us for lunch or out here for more snacks. Thank you.